Today I'm going to be talking about a topic that is very near and dear to my heart, essentially working on reducing video freeze for video conferencing, as I myself have done quite a bit of video conferencing over the last couple of years. So this work is focused on live streaming applications like video conferencing, in which a sender is trying to communicate a video to a receiver. Now, this involves transmitting a sequence of video frames over a lossy network. When we look into this sequence, and we look into the ith frame, this involves sending some data for the ith frame over one or more data packets, shown in blue. The sender may also choose to send some number of parity packets, shown in brown. The issue we're trying to address is packet loss. And in order to maintain a high quality of experience, we need to ensure that these lost packets will be recovered within a low latency. So ideally, these lost packets will be recovered quickly. The problem is that conventional packet loss recovery is not going to be optimal in the setting of video conferencing. So our solution is to propose new streaming codes, which take inspiration from new results in the world of theory to try and do bandwidth-efficient loss recovery within a low latency. And ultimately, we're going to provide improvement over several key metrics for the quality of experience, including reducing video freeze. Now, why is conventional loss recovery not going to cut it for our setting? The first type of loss recovery you might be familiar with is retransmission. And for short-distance communication, retransmission is going to be optimal. However, for longer-distance communication, where the RTT is too high, retransmission is not going to meet the strict latency constraints needed for real-time communication. So what else can we do? Well, maybe we can try replication. And the problem with replication, which would be sending each packet twice, is that it wastes half the bandwidth. So a natural technique that is used by many systems, for example, Teams, is to apply forward erasure correction, such as with block codes. Now, one of the most common types of block codes would be the Reed-Solomon block code. And we'll show an example right here. So you might encode 4 data packets, D1, D2, D3, and D4, together and create 2 parity packets, P1 and P2, with the property that if any, at most, 2 packets are lost, the parity packets and the remaining data packets suffice to recover everything. So this does provide packet loss recovery, but we'll show next how these conventional approaches are still going to be suboptimal in the amount of bandwidth that they're going to require for the specific application that is video conferencing. So let's say that we wanted to apply Reed-Solomon codes to video conferencing. There are 2 very natural ways to do this. The first is maybe we apply a Reed-Solomon code within each frame. So when we send the packets for frame 1, that will comprise some data packets, some parity packets, and they'll all be encoded together. Now the problem is if more than 2 packets are lost, this frame will not be recovered. Now we're employing Reed-Solomon codes within each frame, which means when we send the packets for the next frame, we're going to apply a Reed-Solomon code within the next frame. Now, there are no losses here, but because we applied the code just within each frame individually, the parity sent for frame 1 is not going to be useful for recovering frame 0. Now, this is problematic because it's effectively wasting the parity that is received with frame 1. And this can be an issue because of interframe encoding, which means that you might not even be able to play frame 1 without having frame 0, causing the video to freeze. OK, so here's a problem. How do we fix it? Well, the simplest quick fix is why not just apply a Reed-Solomon block code across multiple frames? So we'll show what it looks like here if we employ it across 4 frames. So we would send all the data for frames 0, 1, 2, and 3. And now all the data is available. We create the Reed-Solomon block code and send all of the packets at the end of the block. OK. Now, does this solve the problem? Are we going to end the talk right now? Unfortunately, we're not. So there's 2 main issues. Let's say that there's just one lost packet during frame 1. Now, because there's only one lost packet, it shouldn't be that much work to recover it. But we can't recover it yet. In fact, we can't recover it until the parity is sent at the end of the block, 3 frames later. If we're having a call at 30 frames per second, the extra latency of 3 frames is going to be about an extra 100 milliseconds. And that was to recover just one packet. The second issue is by sending all of the parity for 4 frames at once, it's going to cause a spike in the bandwidth, which may in fact lead to additional losses. OK, so we've seen 2 examples of why Reed-Solomon codes might be suboptimal. There are alternatives. You might apply a Reed-Solomon code across 2 frames, or 3 frames, or 5 frames. And they're basically going to trade off the 2 metrics of bandwidth or latency, and they'll be suboptimal. What we really want is simultaneously very fast loss recovery if there's just one loss, while also having the parity be useful if there's multiple losses, with the parity sent immediately after. In order to attain this goal, we look to the literature on streaming codes. And streaming codes are designed to have optimal FEC for the following communication model. So in order to reflect the real-time communication setting, the latency constraint is imposed, that each frame will be recovered within tau additional frames. Now, what does this look like? So let's say that we were communicating the first 4 frames, and there was a loss with frame 0. We're able to recover it using the parity of the next 3 frames, which means the latency to recover is 3 frames. Now, this is a systems conference, so when we're talking about latency, what we really care about is time in milliseconds, not number of frames. And it's very easy to translate time in frames to time in milliseconds. So if we're doing a call with, let's say, 30 FPS and a 50 millisecond one-way delay, then the end-to-end latency will be 3 times the time between frames of 33 milliseconds, plus the 50 millisecond one-way delay, so about 150 milliseconds total, which is a standard value one might use for video conferencing. OK, so streaming codes are designed for optimal loss recovery of bursts over B consecutive frames, followed by a guard space of at least tau frames with no losses. And the way that they work is by sending parity packets within each frame, computed over the previous several frames, in order to sequentially recover the lost frames of a burst by their deadlines. So frame 0, in the previous example, would be recovered. So if you have a burst over frame 0 and frame 1, frame 0 is going to be recovered before frame 1. And this is in contrast to conventional approaches. So many block codes, for example, will recover all the lost packets together. So if there's a burst over multiple frames, they'll recover both of the frames at the same time. There are 3 main challenges to using streaming codes. Okay? The first is that they've been primarily developed in the theoretical setting. And so we haven't yet shown that they're going to be suitable for actual real-world losses. Second, there are gaps between theory and practice, such as theoretical works assuming that all packets are lost for a frame, which sometimes does not occur, and assuming that there will always be a sufficient guard space of tau consecutive frames with no losses after each burst. Finally, existing codes have not been assessed in terms of their impact on the quality of experience, but rather assessed in terms of what fraction of packets were recovered, which will tie into the quality of experience, but is not sufficient alone to guarantee improvements. We address each of these in turn, first by assessing real-world packet loss characteristics from a data set of calls from Microsoft Teams. We look into about 9,700 traces from Teams one-to-one video calls from a 2-week period. We assess the loss characteristics in terms of their burstiness. Now, there are 2 main factors that we care about when it comes to bursts. The first is how many consecutive frames were involved in the burst. And by involved in, I mean had at least one packet lost. The second is when this burst occurs, what fraction of the packets were lost? If we have 2 consecutive frames, and they each send 10 packets. If we have 2 consecutive frames, and they each send 10 packets, did we lose 20 packets, or did we lose 2 packets? These two scenarios are going to be very different for how much redundancy is needed. Finally, we assess the guard spaces when these losses occur. So how often did we have at least tau consecutive frames with no losses? Why tau? Well, with streaming codes, we're looking for bounded latency. So if each frame is recovered within tau frames, once you have at least tau frames in the guard space, you don't need any longer guard space because everything's been recovered. Throughout this talk, we'll consider tau equals 3, which is set from the early example of 50 millisecond one-way delay and 30 FPS to try and bound the end-to-end latency at about 150 milliseconds. So when we looked into the burst characteristics, we assessed looking into each of the bursts over all the calls. And we look at how often the bursts encompassed 1, 2, 3, or more frames. What did we find? First of all, there are a lot of instances of burst losses over 2 to 4 frames. Now, this is going to be crucial for us because if we're targeting the worst case losses, that will enable us to recover less bad instances of loss. So if we can recover from a burst of 2 frames, then we should also be able to recover from a less bad situation, like a loss of just 1 frame. And a lot of the instances of loss of bursts of 1 frame will be, for example, just a single lost packet, which should be easy to recover. However, with traditional theoretical streaming codes, the amount of redundancy employed is going to be based on this maximum length of a burst, b. But it's not immediately clear how we would set the maximum length burst, given that there are occasional longer bursts here. We also assessed what fraction of packets are lost per frame. Is it the case that whenever there's a burst, every single packet is lost for every frame in the burst? No. It will vary from at least 1 packet lost per frame, but that can be a very small value, close to 0, all the way up to sometimes all the packets are lost. So the previous model of everything being lost is often pessimistic. When we assess the guard spaces, we find that it's very prevalent to have sufficiently long guard spaces, but it's not always the case. So we will need to address some of these gaps when we design a new system to use streaming codes. And that's what we do. We introduce Timbre, a new communication paradigm for video conferencing. Now it will combine 2 things. First, a new streaming code that we'll describe shortly, and a lightweight binary classification model, which will be set to use the amount of parity packets that are sent. Now, I won't get into that in this talk, although I encourage you to see the paper. But essentially, this will solve the problem that existing codes set the amount of parity packets based on these parameters b and tau. That won't really apply for this scenario, so we use an ML model to handle how much redundancy is set. And you can think of this as taking the amount of parity that is sent by an underlying system and either sending the same amount or reducing the amount that's sent by 50%. And again, please see the paper for details. So the components of Timbre within the broader system are shown here in green. Timbre will handle taking the data of the video frames and will recover lost packets and feed the recovered data back to the video decoder. It will also employ periodic feedback of, in this example, just this very small amount of feedback to indicate how much parity should be sent for the next period based on recent packet loss characteristics. So let's get into an example of how Timbre recovers from losses. So the first frame is sent, and the data packets are still sent for the frame in the same way. But we're going to label half of them in green. And the reason for this is that the parity packets sent for the current frame and the next 3 frames will be useful if these packets are lost. For the other 2 packets, they'll be in blue, and they'll be recoverable using the parity for the current frame and the one sent at its deadline 3 frames later. So let's say there are losses with frame 0, and there are losses with frame 1. If there are no losses with frame 2, then the parity for frame 2 are used to recover the green packets of both frames. Next, frame 3 is sent, and it is used to recover the final missing packet of frame 0. So frame 0 is recovered within a latency of 3 frames. Frame 1 is not yet recovered, but that's OK, because frame 1 doesn't need to be played yet. Now frame 4 is sent. its parity packet is used to recover the final missing packet of frame 1, meaning that frame 1 is recovered with a latency of 3 frames. OK, so far, we've looked in kind of the worst case loss scenario. And we've shown that now streaming codes can leverage the parity in the guard space after the frame for loss recovery, avoiding the problem from Reed-Solomon codes within each frame of wasting this parity. Next, we address the other issue, which is what happens when there's just an occasional loss. Well, we'd like to have loss recovery with minimal latency in this scenario, unlike a Reed-Solomon code across 4 frames, which might recover with a latency of an extra 100 milliseconds. And what we find is that Timbre is designed so that if there's just one loss, it will be recovered immediately, addressing the second goal. Next, we evaluate Timbre by first implementing it in C++ and releasing it online, and integrating it with Ringmaster, which is a new video conferencing platform for emulating one-to-one calls. We compared to 2 baselines, which will use slightly more bandwidth for parity packets than Timbre. Block within, which is a Reed-Solomon code applied within each frame, and block multi, which is a Reed-Solomon code applied across 4 frames. We evaluate over 80 10-minute video calls at varying bit rates over Mahi-Mahi using emulated networks, the full details of which are in the paper. So when it comes to the quality of experience, if it's going to be degraded from packet loss, that'll happen for 2 reasons. Either because we're not rendering frames, or because we're rendering the frames, but at an increased latency. When it comes to not rendering frames, we assessed the percent of frames for each video that were not rendered, and looked at the percentiles over the videos. And what we found is that Timbre offered significant improvement. So for example, reducing the median, at the median, reducing the frequency of non-rendered frames by 73% compared to one baseline, and by 28% compared to the second baseline. In terms of the latency, there is a small cost compared to block within of an extra about 6.5 milliseconds, which is insignificant compared to how much improvement we get in terms of rendering frames. We also are able to reduce the median latency by almost 19 milliseconds compared to block multi. And that's by recovering occasional losses within the same frame. Next, we assess video freeze, because video freeze is another key metric for the quality of experience that will affect the gold standard, which is the mean opinion score. So we looked at the frequency of video freezes. Again, we looked at the frequency for each video call, and we looked into the 25th, 50th, 75th percentile. What we're able to show is that Timbre reduces the frequency of freezes by 78% over one baseline and 26% over the other baseline at the median. In summary, during our online assessment, we found that Timbre is able to simultaneously improve several of the key metrics for the quality of experience of video. So, in this work, we address the challenge that conventional loss recovery is going to be suboptimal for video conferencing. The way that we did this was we built Timbre, which combines us designing a new streaming code with employing a lightweight ML model to determine how much bandwidth overhead is allocated to parity packets. The outcome is taking us from the before setting of having more frequent instances where the receiver's video is frozen to now applying Timbre, reducing 26% of the freezes and 28% of the rendering failures, and hopefully leading to higher quality video with less freeze. Thank you.